Good morning. Good morning, everyone. So let's continue with simple harmonic motion from where we left off yesterday. Again, reminding you all what we learned about yesterday is that for SHM, that is for simple harmonic motion for a particle on a straight line, we would have the total external force acting on the particle, which we call the restoring force, okay, is equal to minus k delta x, right? That is, the total external force is proportional to the displacement but in opposite direction to the displacement. And similarly, a relation about acceleration is that acceleration would be again proportional to displacement but in opposite direction. So these two things are what we should look for when we are talking about simple harmonic motion. Okay, so now let's discuss more details about this kind of motion. Now, first of all, let's try and imagine how the whole thing is going to work. Okay, let's try to see what happens as the particle moves. So last time at the end of the class we talked about what happens at the mean position, right? So we figured out that at the mean position we are having the displacement 0, and that's why the external force is 0, acceleration is 0, right? We call this mean position also as what? What's the other name for mean position in simple harmonic motion? Yes, it is also called equilibrium position because at that point the total external force is 0, right? Okay, so now let's go over to the other part, right? Once again, I'm drawing the diagram here so that we keep in mind what's going on. So let's say here is that line on which the particle is doing SHM. Here is the mean position, which is origin or 0, right? Because we measure displacement from here. Let's say here is the extreme or the end position, and here is the other extreme or the end position. So now, we talked about mean position, that's done. Now let's go to the extreme position. So let's discuss what happens at extreme position. Okay, that is at the end point of motion. So first thing to understand is that when the particle is here, right, let's say the particle moves and reaches here at this particular point. At that point, the displacement at the extreme position is plus a or minus a. This one for plus a, right side generally we take it positive, left side we take it negative normally, right? So what does this A stand for? A stands for amplitude of SHM. Okay, A stands for amplitude of SHM. If you want to write a proper definition of what is amplitude, it is something, amplitude first of all indicates maximum kind of behavior. Okay, so amplitude means maximum displacement from mean position. Maximum displacement from mean position in any kind of oscillatory motion, including SHM, of course. Okay. Right, in any kind of oscillatory motion, oscillatory that is going back and forth, right? So whenever there is any kind of oscillatory motion, then the maximum displacement from mean position. So if you think this is the mean position here, then the maximum displacement can be here or it can be here on the opposite side. So that maximum displacement is called amplitude. Okay, definition clear? The symbol of amplitude is capital A, like I have mentioned here. So when the particle goes to this end position or the extreme position, the displacement is plus A. When the particle goes to this end position, the displacement is minus A. Everything over here clear? Okay, very quickly, can you tell me how much will be the distance between the two end positions or two extreme positions? Can you tell me how much will be the distance between the two extreme positions? Well done, 2a, very good, 2a. Okay. Let's write more things about extreme position. This extreme position is once again like one of the special positions. Just like mean position has something special going on, at extreme position also something interesting is happening. If you remember earlier, I did mention that suppose here is the particle P which is moving. Let's say it's going on the right side. It will reach E, and then it will have to turn back. You understand what I'm saying? So suppose the particle reaches E, and then at E it will have to turn back. Did you get it? Right? At E it will have to turn back because this is the maximum displacement. It is not going beyond that. Now that clearly means that the velocity at the extreme position is 0. Is that clear? Reason, direction is reversed. You know, whenever directions are reversed, for one moment over there, the speed, the velocity must become 0. This is similar to the cases. Toss the pen up, toss the ball up. At the highest point, the direction is reversed. Okay, so that point, the speed should be 0. Absolutely clear? Okay? Right. So remember this as a rule. At extreme positions, both, right? Not just one side, both sides. At extreme positions, V is equal to 0. Okay? That's something worth remembering. Right? At extreme position, V is equal to 0. Where is acceleration 0? Where is acceleration 0 in SHM? Very good. At mean position, acceleration is 0, and at extreme positions, the velocity or the speed is 0. Right? So please be careful about that. Okay. Now, how much is the acceleration or the force at at the extreme position? Let's talk about force. Okay, total external force in magnitude only. Okay, at the extreme position will be K into A. Is this understood? K into A. Why K into A? K. Displacement A. Why not minus magnitude, like I said? Okay, this is only in magnitude. Because at one point the direction of force will be towards left side. At this other end point the direction of force will be opposite. So that's why I am not claiming anything about direction. This is only in magnitude. Okay? Of course, this is the maximum force. You see, you should understand that this is the maximum force, right? Or maximum net force. Why maximum? Simple reason. Delta x. Where is delta x maximum? At extreme position, isn't it? Right? Delta x is maximum at extreme position. That's why total force or restoring force is also maximum at extreme positions. Got it? Okay? See, all these are very simple, very short points, okay, about SHM, but they are really useful when you are trying to solve questions. Okay, everything written on the board right now is most important for this chapter. I repeat, everything that is on the board at this moment is most important for this chapter. Clear? You cannot afford to forget any of the lines on the board right now. Okay, let's go over to the next thing. Obviously, if force is maximum, do you realize that the acceleration will also be maximum? Right? So we can say that A max, okay, maximum acceleration is going to be K into A upon M. Is that fine? K into M upon A. Clear? Right, now what is K upon M that we have not discussed yet? I just want you to leave a little bit of space here so that we can write one more thing. Okay, we'll talk about that later. Right, so again, where is the force and where is the acceleration maximum? At the extreme position, and speed is minimum at extreme position. Speed is 0. Okay, vice versa. I hope you are seeing that. At mean position, force and acceleration are 0. Right, but at extreme position, force and acceleration are maximum and speed is 0. Okay, fine. Hopefully you have noted everything down. Let's proceed. Okay, now before we can analyze or we can go through with more detailed maths of simple harmonic motion, we will have to go through a few basic differentiation rules. Okay, don't worry, we have gone through it earlier. This is just a revision. Okay, so d by dx of sine x. Do you remember this? Anyone? D by dx sine x. Okay, what is the velocity at mean position? We will talk about that later. Okay, it is cos x. Very good. D by dx cos x is d by dx cos x is minus sin x. Okay, right. These are the two very basic things that we need to know. Now it comes to the chain rule. Okay, right? The chain rule. Now what is the chain rule? Is that, if you remember, I have told you that there are some situations where you get things like this. So you cannot use that formula directly, n x raised to n minus 1. So must do it like this. Is this clear? Whether you have opted for maths or biology, you don't have a choice. You have to learn this. Okay? Of course, you can, wrongly think as if you are cancelling these two. Okay? Is it fine? I know it's not correct. I know it is not correct, but that's an easy way to understand what's going on. Easy and slightly wrong. Okay, anyways, but you see why I'm bringing this here. We need this. Let's see how. Suppose you want to do differentiation of sine t, then that's very easy. It is cos t, right? Just like here. No big deal. But if you would change this now to something like this. Okay, why this? That will come in the physics of the chapter. Okay, we'll see why we have to do something like this. So when you have it like this, the problem is that this is t and this is not only t, it is omega t. Clear? This is not just t, it is omega t. So what we are supposed to do is, first of all, and go through the basics. We will have to call this like theta. So then this is d sine theta by dt. But I am not going to write that. Okay, because if I write it that way, I cannot do anything with it. Did you understand this step? We are going to take theta equal to omega t and then we write this. Is this step clear? Say yes or no. This chapter completely depends on this. Okay, if you have not understood, I'll have to go through it again. Okay, let's repeat. So, what did we have? We have d by dt sine omega t. We want to find this. The problem, like I said, is this is only t and this is omega t. So, what are we supposed to do? When these things are different, you assume something here. So, we are saying that let theta be equal to omega t. Right? You cannot ask me why theta, it is my choice. Clear? This is let. Hopefully, you know the meaning of let. So, this is d sine theta. And then instead of writing dt, I am writing into d theta by dt. So, this makes perfect sense just like earlier. So, this is the chain rule. Now, this we can do easily. It is cos theta. And then, over here, I am going to put theta's value back in form of omega t. Okay, second step clear to everybody? Okay, now, so cos omega t, over here this is easy. Omega is generally a constant, okay? Omega is a constant, so if omega is a constant, you can kick the constant out and you can write this as omega into dt by dt. And I am sure my learned students remember what is dt by dt. It is 1, okay? You can't cancel it, actually you should not do it that way. dt by dt is 1, okay, right? So this is our final answer, omega cos omega t. But I know some of you would be cringing at the fact that you have to go through this every time. No, there is no need. There is a shorter version of this. What you can do is that if t here is multiplied with omega, then directly you can just multiply that omega outside, it gives you the same answer. So what I mean to say is as follows, that if we want to find differentiation of sine omega t, okay, what we do is, first of all, you ignore what is here, just look at this formula, differentiation of sine cos. So cos omega t, this is not complete yet, but what I have done is clear so far. This is not complete. Is it clear so far? Yes, Ami, you can write d theta by dt as omega ultimately. That's what happened, right? I hope you are seeing that. Okay, now what to do? Then you see that what is multiplied with the omega. Okay, is that constant? Yes. Then just multiply this omega outside on the answer side. Did you get that? Okay. Omega is multiplied with t, so I multiplied omega outside over here, right? That's how you can do it in short. So why don't you try this? Come on. Can you tell me what will this be? Hurry up. Okay, most of you have got right answer. Well done. The answer is 4 cos 4t. Again, stepwise. First of all, you see sine. Okay, sine differentiation cos. So cos 4t. Don't change the angle. And then because t is multiplied with 4, which is a constant, you can put it outside. Okay, right? This is, just a basic version of the chain rule. Of course, the actual chain rule can be more details, but we don't need to worry about all that. So this is 4 cos 40, right? Why don't you try this one now? Can you tell me what's the answer? Okay, just be careful. First of all, differentiation of cos is minus sine. Okay, that's the first step. And then we are seeing, listen to this carefully. We are seeing that t is multiplied with 3, no, with minus 3. Is that clear? T is multiplied with minus 3. So multiply this thing with minus 3. So final answer will be 3 sine of minus 3t. Did you understand? Minus plus. Okay? Be careful. T is multiplied with minus 3, not with 3. Okay. So this is the basic maths that we need. Right. I'm going to erase everything on the board now. Okay. So reminding you of what I taught you yesterday is that some things like sin theta and cos theta, they are such that their values get repeated after some fixed change of angle. For example, in sin theta, it will get repeated when theta changes by 2 pi or 360 degrees, right? Okay, so that's the key thing here. That's where we are going to start. Now we are looking for, why are we doing the math? We are looking for an equation that will make simple harmonic motion. What I mean to say is, what does the equation of simple harmonic motion look like? Does the equation of simple harmonic motion look like this? Or does it look like this? What does the equation of simple harmonic motion look like? That's what we want to find out. Okay, obviously it doesn't look like this. Why? Because simple harmonic motion is supposed to be oscillatory and periodic, right? It should go back and forth, back and forth. This is not periodic. Do you see? This is not periodic. There is nothing here that can repeat itself. Okay, so we should be looking for sine and cos. That's the only way to make equation for simple harmonic motion. Okay, using sine and cos is the only way to make equation for simple harmonic motion. Now, the basic idea is that we want something that satisfies this relation. We want something that satisfies this relation. Okay. Let's, for the sake of mathematical simplicity, consider that mean point is origin 0. Right? This is extreme plus a here and minus a. Okay. So if I am going to say that here is the particle, then its x coordinate will be x. Is that fine? Okay, so if you are measuring the displacement from origin, you can also write this as this. Is it clear? Say yes or no if you understand what I am writing. If mean position is origin, then A is proportional to minus x minus 0. Clear? But x minus 0 is x, right? There is no need to write x minus 0. Understood? Okay, x minus 0 is x. So, if, it's like I'm guessing. I'm making a guess. I know that to make periodic motion I need something like sine or cos. So suppose I would guess something like, let's say x is equal to sine t. Okay, let's say I guess that x is equal to sine t. What would happen? We should check. Do we get this? If yes, we are happy. Otherwise, this is not essential. Let's try. If x is sine t, what is dx by dt? Means velocity. Dx by dt will be equal to cos t. Okay, but here it's about acceleration. From velocity, how do you find acceleration? From velocity, how do you find acceleration? Yes, by doing differentiation. Very good. So, A is equal to dv by dt, which is equal to d by dt of cos t. Okay, what's d by dt cos t? It is minus sine t. And tada! See what have we got? What's A? ID निकाला कि नहीं निकाला? Is this the correct I card or not the correct I card? Okay, so we are seeing that the I card is valid. What does this mean? It means that an equation like this would be representing simple harmonic motion. But equation like this, of course, is not simple harmonic motion. Equation like this is simple harmonic. Fine. Okay, this is just, frankly speaking, this is just baby steps, right? We still have more things to do. Let's change a few things here. Suppose instead of x equal to sine t, suppose we have x equal to sine some constant and t. Okay, I am going to call that constant omega. Right? Why I am calling that omega? Don't worry too much about that at the moment. Okay? So let's say I would put some constant omega, right? Omega is constant. So now let's do the procedure again. Suppose it was like this. Would we get the same kind of result? Let's check. First of all, we find v. So v is just dx by dt, means differentiation of sine omega t. We have just done it before a while, so I am not going to spend any time writing the answer. Okay, so we get v equal to omega cos omega t. Fine. Let's find acceleration. A is equal to dv by dt. So that is differentiation of omega cos omega t. Remember, this is angle. Okay, you cannot separate anything out of that. We have to differentiate this. First of all, omega into cos. Omega is a constant. Kick the constant out. Therefore, A is equal to omega outside and d by dt of cos omega t. What is differentiation of cos omega t? We just saw it before a while. Come on. What is differentiation of cos omega t? Hint, it is not minus sine omega t. I repeat, differentiation of the entire cos omega t is not minus sine omega t. It's something else. What is it? Yes, it is minus omega sine omega t. Did you understand? It is minus omega sine omega t. Same rules as we learned earlier. First of all, differentiation of cos will be sine, but here t is multiplied with omega, which is a constant, so multiply omega outside. Okay, and then the differentiation of cos is minus it. Sorry. So finally, this is minus omega squared sine omega t. Here also, we are getting this kind of behavior. Let's see why. Omega squared is a constant, isn't it? Because omega is constant, omega squared is constant. But what is sine omega t? It is x. So, based on this equation, do you realize that here also I can write A is equal to minus omega square x minus omega square x and because omega is constant, I can write this. So once again, we have the I-car, right? So that means equation like this also, where t is multiplied with some constant. Equation like this is also SHM. Is that fine? Equation like this, where t is multiplied with some constant, is also SHM. Okay? Fine. Now, this is not it. We can change it even more, right? But that part I am not going to show on the board. I'll just do it directly. Gives you the same kind of steps. It's not just that you can write omega t. You can actually write one more constant here, right? Okay, you can actually put one more constant here. Suppose you write something like omega t plus phi 0. All names will come later, of course. Okay, there is a meaning associated with each of these symbols. Okay, so even if we write x equal to sine omega t plus phi 0, where once again omega and phi 0 both are constants. Okay, just adding some constant never makes changes to the differentiation. So even in this case, we are going to get the same kind of relation. Okay, there is no doubt about it. You can go through the steps if you want. You are going to get the same. Clear? Okay. One more variation possible. It is that instead of sine, suppose you do it with cos. Suppose instead of sine you do it with cos. What difference would it make? Okay, well, nothing. Just that the differentiation would change the order. What I mean to say is, if you find v, first of all, v is dx by dt. Then differentiation of cos will first of all be sine. So minus omega sine omega t plus phi 0. Okay. So earlier we were getting, if you take x equal to sine something, you get v is cos something. But here if you take x equal to cos something, then you get v equal to sine. And then acceleration is, once again you differentiate this, so you are going to get minus omega squared cos omega t plus phi 0 by doing differentiation one more time. So once again you will get the same relation. Okay. So all this that we have talked about so far is telling you that any kind of equation, either of this type or of this type, equation of this type or this type, gives you simple harmonic motion, right? One more change that we can make is, suppose instead of writing nothing here, let's say I write 2. Then it's just like I'm multiplying everything by 2. So the final result will still remain the same. You get what I'm saying? Multiplying a constant once again will not affect anywhere because everything will get multiplied. So we still get the same result finally. So the most general formula is for SHM, x equal to a sine omega t plus phi 0. This is the most general formula for SHM. Okay, you can adapt this in any form. You can also write cos. Remember, math students will realize that you can easily convert sine to cos if you want. Okay, so you have two choices actually, depending on situations. Sometimes we use this, sometimes we use this, as we may prefer. Okay, right? So this is what the equation of simple harmonic motion looks like, because these kind of equations satisfy this relation. Okay? Understood? Well, now enough of maths, I think. Time to understand what happens as something is doing SH. Okay, the physics part. Okay. So let's say that this is mean position, origin, right? Okay, just one thing here. Please write a note. If mean position is not origin, if mean position is not origin, then replace x by delta x. Why so? If you recall how we had come to this point, it's that if we take mean position as origin, then instead of delta x we wrote x minus 0, and that's how we got x. So truly speaking, in general form it will be delta x. But like I said, mostly we will find that we take mean position as origin. I repeat, mostly we take mean position as origin. So it's fine. This is only a rare possibility. Okay? Yeah. Let's start. So I was saying that here are the two endpoints or extreme positions. This distance is a, right? So this point is plus a, and this point is minus a. Right side positive as usual, and left side negative. Now suppose a particle starts from, let's say, this position, end position on that side. It could start from anywhere, right? It's just a case of which one we want to describe. Now, this is just a diagram for indicating what's going on. You can compare it with a physical situation, a physical system like this. This is a spring that has been stretched. Okay, here is a mass m. This much length is the natural length of the spring. Okay, and you could say that it's not going to hit over here, right? So what we want is that if you will pull it, observe this carefully. Earlier the block was just here, okay, but we pull it. Okay, so now it has come to this extreme position, and now we are going to let it go. We will release it, so its initial speed will be 0. Understood? Clear or not clear so far what I have described? Again, here this is the line where there is natural length, okay, and if we drag this spring out, we pull it, we extend it, we bring it here, and then we release the block. So what will happen to the block? In which direction will it start moving? In which direction will the block start moving? Left side. Very good. Okay, so it will start to move towards left side, right? But you see, as it moves towards left side, and it comes to this point, okay, so now it has come to this point. Let's say after some time over here, this spring will be natural length, correct? So how much is elongation over here in this diagram? How much is the elongation of spring? How much is the elongation of spring when it comes here? 0, well, 0. If elongation of spring is 0, do you realize that force by spring is also 0? Right? So you see what has happened is that this has come to the mean position or the equilibrium position. Again, it has come to equilibrium position because of course there is nothing else that's applying force. Smooth surface, okay, ideal case, right? So when it comes to this line, the force on it becomes 0, so it is an equilibrium. So you see, if force is 0, that does not mean the object stops over there. Elongation is not natural length. Be careful. So I am saying that when it comes here, the force is 0, but speed would not be 0. Reason, the spring would have pulled it and it would have brought it here. So now it will overshoot. I am saying that it will not stop here, it will overshoot. Did you understand that? I am saying it will not stop here, it will overshoot. What is meaning of overshoot? It will go on the left side. It will not be able to stop over there. Okay. Yeah. So now if it will overshoot and it comes on the left side, you're going to see that the spring will start getting compressed. Right? The spring will start getting compressed. So let's just draw a new diagram quickly. So ultimately, as the spring starts getting compressed, the block will be able to move all the way from here to up to this point where it will stop. Can you imagine that for one moment here the block will stop? Clear? Clear or not clear? Because the spring is pushing it. Okay. Fine. So it will stop. Then will it always remain here? Will it just remain over here? What will happen after this? Will it just remain over here or not? What will happen after this? What will happen after reaching that point? Yes, it will start moving towards the right side. Very good. After that, it will start moving towards the right side because the spring is continuously applying force on it, pushing it, right? So you see this over here, right? This over here is exactly what SHM is. Let's see how. When the displacement, at the start this block was here. At the start the block was here. So displacement from mean position was in this direction. At that time the spring was stretched. I repeat, at that time the spring was stretched. So what happens over there? Because the spring is stretched, it will try to pull it back. Do you see that property? Displacement and force on the block are in opposite direction. Yes or no? Okay, Amrita, I'll answer your question very shortly. Right? Okay, so the question is, why did it overshoot? Why did it go ahead? Well, think about this, the answer lies here. Over here, this was at rest, correct? Okay. Now the spring force is acting towards left side. So gradually the velocity will increase towards the left side, correct or not? And till this point, between E and M, the force by spring is always towards left side. Do you agree, everyone? Between E and M, the force by spring will be towards left side. Yes, no? Parthra, you are giving answers based on the knowledge that you have gained from somewhere else. Okay, you are not answering by basics. Not bad, but try to clear the basics as well. So, if spring force is always towards left side, do you realize that when the particle will come here at mean position, its speed will not be zero? Yes or no? Do you realize that the particle's speed will not be zero because force was acting towards left side? It has increased its velocity. Okay? Right? Ankita, I hope that's clear. So, because it has velocity towards the left side, it will overshoot. You know, objects move in direction of velocity, not in direction of force. Okay? So, here the object will overshoot. It will come towards the left side. Right? So, then what will happen? The force will try to stop it. So, it will slow it down. So, between M and E dash, anywhere between M and E dash, the force is always towards right side. Is that clear? Because the spring is compressed. Because the spring is compressed. So, we are seeing all characteristics of simple harmonic motion in this motion. Hopefully, you realize what I am saying. Right? Why? First of all, we are seeing that the total force and displacement are in opposite direction. The second thing we are seeing is that because this is force of spring, see, if you remember, spring constant, force constant. Here, this is an opportunity for us to see how they are same or how they might be different sometimes. Here, force of spring. You know, force of spring is always equal to K into delta x in magnitude. Right? And if you consider the direction, then it is in opposite direction of elongation. So you see, what we are having here is that the spring force is actually following the same pattern, right? Same pattern as what? As required for SHM. You understand what I have written here? Follows the same pattern as required for simple harmonic motion. Okay? Okay or not okay, everyone? Force opposite to displacement, correct? If spring is pulled right side, spring force left side. Okay? Not only that, spring force is proportional to elongation. But here elongation is measured from natural length, which is the mean position. Okay? Right. So this is one of the simple examples of simple harmonic motion. Right? This is one of the simple examples. Yeah. Okay? Vice versa is it true for last sentence? What do you mean? Do you mean to say that spring is required for simple harmonic motion? Is that what you mean, Ankita? Do you mean that spring is required for simple harmonic motion? No, not necessary. Okay, not necessary. There are some other cases or other kinds of situations where even without a spring we can get this kind of behavior. Right? Where even without a spring we can get that kind of behavior. Okay? We will cover some of those behaviors or situations in this chapter. Okay? But yes, the easiest is spring. There is no doubt about it. Right? Okay. Right? So I think this is a physical example of what SHM looks like. Just try to imagine how a spring moves. It will start from rest. From here, spring will pull it, it will move here, it will overshoot, it will slow down, stop here, then it will go back, okay, like this, and then back, like this, and this, and this, and this, okay? Understood what SHM would look like? Okay, keep that imagination going, right? Fine. So now we will continue with this the next time. Okay. So goodbye till then.